Well, welcome back to the channel. Hope everybody's doing well, and in today's video we are taking a look at this insulation tester from Chauvin Arnoux, the CA6543, and in the UK this will set you back a cool £1,842, making it the most expensive basic sub 1000 volt insulation tester out there that I could get my hands on. And when I say a basic insulation tester, I'm talking about a tester that has the insulation test function along with a continuity function, and that's pretty much it. Certainly you can have the DAR and the Pi, that's all part of insulation, and it has those functions as well. There are other instruments out there such as the MTR105 that do cost more than this, but the MTR105 has an awful lot more functionality built into it, hence justifying its higher price. For your money, obviously we can see the insulation tester here, which is a fairly sizable unit. In comparison to standard insulation tester, you can see just how big it is. With the accessories, you get the 3 crocodile clips here, you get the 1 probe, you've got a communications lead, that's your serial port, and then we have a bit of paperwork, just some safety sheets. The actual manual itself, the manual is also available in PDF format and it's in multiple languages. You then get like a quick guide card that is again available in all the languages. You get a laminated sheet for each language there, so you usually only need 1 of these with you, and the rest can be stored. You do not really get a calibration sheet, you get a declaration of conformity here. There's no real calibration data in there or anything like that, but you do get that. And then test lead wise, we've got the blue and the red because this has a guard terminal, and we do get a black lead as well. This black lead is a guarded lead, so it has a shield running up inside the lead around the conductor. And then you get a mains charging lead that is not UK compatible. So you're wondering why this costs so much. If we zoom into the lid, you can start to see a little bit why. And this is the main reason why. You can see the capabilities of the unit on the label inside the lid here. 50 volts, we can measure up to 200 gigaohms. That is pretty much the range I find on the best of the other insulation testers at 1000 volts. That's the max they can go to for their highest voltage. But this can do that at the lowest voltage. 100 volts, you double that to 400 gigaohms, and then we start getting to teraohms. All the way up to 1000 volts, it can get up to 4 teraohms. So fairly extensive measurement range built within this unit. And our accuracy on these, up to 40 gigaohms, we are plus or minus 5%, and we are plus or minus 15% above that. Based upon my accuracy testing that I've completed on this unit, the average accuracy comes out as 0.562%. So we're operating way within those parameters. In comparison to other insulation testers, it's sub 1%, it's fairly much there. You can see it in the graph there, fairly reasonable, although it isn't the most accurate of instruments that I have tested over the years. So I'll just demonstrate the continuity function on the instrument. To get to that, we've turned the dial switch round to the 40 ohm mark there. I have wired the output through this multimeter set up as a milliamp meter, so we can verify the current, which should be in excess of 200 milliamps. And we can check the resistance of the winding simulator here, which in delta configuration should be 1.17 ohms. So if I just short the leads out on their own at this moment in time, hit the go button, we should be measuring the resistance of the shunt inside this instrument, and you can see we are getting 242 milliamps there and 2.05 ohms. Now we can null that out if we go around to the setup function and wait for that to boot through, and then if we hit the button 3 times, you can see we are set on, but it's set to 0.27 ohms, which is these leads on their own really. So we short it out and hit the go button again. We'll do its little calculation. So it's going to take 2.31 ohms off, go back to our continuity function, and then we can go across one of the windings. Oops, stays on. Go button again. And we've got 1.17 ohms dead smack on. I'll try one of the other ones. 1.18, 1.19 ohms. So that's all good, and we've still got our 240 milliamps going through. Obviously every time you change the leads you're going to have to go back to the setup function to change the null value. Overall, messing around with this, didn't do too well with the continuity function. I got 4.82% overall accuracy. That's across this winding simulator in all its different configurations, measuring at all three phases. So in my league of insulation testers, this is quite close to the bottom in terms of accuracy in its continuity function, which was quite a surprise. So we switched over to our 500 volt insulation test function there to show you the output voltage of the instrument. You can see at this moment in time that I'm actually plugged into the mains, and we are actually charging the battery. So this instrument can charge the battery and operate at the same time, which is an added bonus for these kind of instruments, with the battery embedded within inside the instrument and not changeable. We've connected our key sight directly across the output of the tester, and we switch to DC voltage and press the button here, and you can see we are putting out 520 volts, 516 volts now, 515, 10 mega ohm reading. That's typical for the DC function on a multimeter, and with 517 volts on our key sight here, so fairly accurate voltage measurement coming from the instrument. I can put up this plot here, which is the output curve of the instrument at 500 volts based upon the loading of these terminals. It's in comparison to the MIT 420 and the key sight meter here, and you can see both at the lower end of the load values. You can see that the voltage output is seriously affected on those two instruments, whereas on our CA6543 here has a pretty flat curve across the output range. That is predominantly because of the higher short circuit current that this instrument can provide. I'll just switch off and swap this around so that we go onto the current measurement function. And it goes there. We'll force the So force that to the 6 milliamps there, and we'll go for a short circuit test again at 500 volts. And you can see we're actually kicking out 4.9, 3.3 milliamps there. So yeah, whilst the instrument stabilises, we've ended up with a 3.3 milliamp short circuit current out of this. Generally speaking, 1000 volt insulation testers operate around about 1.5 milliamp short circuit current, so this has greater output capabilities. That's quite handy if you're testing on cables which are capacitive in their nature. This instrument will charge that cable up a lot quicker and easier than an insulation tester with a lower short circuit current capability. And I can just put up this quick little plot here. You can see the short circuit current capability across the whole range of these insulation test functions within the meter, and you can see they're fairly consistent across there. So the instrument seems to have quite a good regulation circuit on it. So I'll have a little demonstration of the polarization index function on this insulation tester. See, I'm connected up to my winding simulator here, onto the earth, one connection onto the winding, and there are three ways that I can record the polarization index test using this instrument. You see down here we have the RDR PI button. I can cycle through these to select the function I want. There's PI, back to normal, on off on the button here. So if we select PI mode there, we can hit the go button, and you can immediately see I've got the test voltage come up on the screen, but we're not responding to any mega ohm value. To get the mega ohm value, I have to press this button again, and I can cycle through, and there you can see I've got some mega ohm readings, no DAR, no PI ratio. Go back to there. I can also, whilst I am In the test mode, use the V time button up here, and instead of 267 volts, I get the time duration for the insulation test. So now that we've just gone past the 1 minute DAR ratio value, I'll just show you that during the PI test it does record the DAR value as well. And if I use my R DAR PI value button to cycle through, you see I've got my mega ohm readings there, and now we actually have the DAR ratio of 1.62, and then go back and it will record the pi ratio at the end of the test. So I do have that value available for me, which is a nice feature to have on an insulation test. It saves me doing a DAR and a PI test separately. And you can see with displaying the mega ohms reading at the same time as the duration of the test, I'm able to record that value manually on paper, of course, but I can record it for whatever time interval I require for my test data. So we are coming up to the end of the test now. What I am going to do is remove this lead when the test is finished, because it will see the charge left on the instrument. There we go. I'll remove that there, and you can now see I've got the PI value there of 7.42, and I can cycle through my R, DAR and PI. So there's my DAR value of 1.62, there's my PI value again. I do get the capacitance on this as well. That's an automatic calculation at the end of the test, but you only get that at the end of the test. And there's my mega ohms reading. If I didn't pull the lead off and I left it for any significant period of time, I think beyond 15 seconds, with the charge still seen on this, I will lose this data and I won't be able to cycle through it. So if you've got a highly capacitive object, you must remove the lead after the end of the test, otherwise you will lose this data on this button here. So that's the first way that I can record the PI value. The second way is to use this time function here. So if I go hit enter there and there, you can see that I've now moved to a time function. To set up that time function, I need to go to my setup, which is up here. Let me work through that. And then I select time function, and this will be the total duration of the test. It's currently set to 1 minute, but I need 10 minutes for PI, so I'm cycling them up through this button here. You can also go down. If you hit second, you can go down as well. But we need to get this up to 10 minutes. So we can then enter that there. They also have a time interval as well, so if I go second again, and time interval. So this is going to record the value at every 15 seconds. Again, I can change this if I want to in the second values, but 15 seconds is good enough for me. So we can enter that one again. Go back to our 250 volts test, and then I will need to leave this shorted out for a duration. Let's just put them on there. So yeah, so we're at 70 volts, so I'm going to have to link this out to get rid of the charge, and then when that's sufficiently drained, I will be able to restart the test. So we'll just check that we are fully discharged now. Yep, that's okay. So we can go back to our setup, hit the second button and the timer there, and then we can hit the go button again, and you can see we get a time up. On this occasion we are now counting down on the time, and we automatically get our mega ohms reading on there. So again, we can leave this to work through the test, and then we'll convene at the end of the test. So coming up to the end of this test now, and again I'm going to have to pull the lead off to collect the data, otherwise it will go into, and there we go. So that's the test over with. We've got our 33.19 mega ohms again, my R, there's my DAR value, there's my PI value, there's my capacitance value, and there's my mega ohms again. However, because I've used the timing function, I get extra data off of this RT function here. If I go second, RT, you can see my display has changed, and I've got the mega ohms value at 15 seconds. I can then use this button here and scroll through. There's my 30-second reading, there's 45, there's 1 minute, 1 minute 15, and I can work my way through these and write down any of the values that I want at a specific time and record the data in that manner. As long as I don't switch anything off or change settings or restart the test, I will be able to keep looking at this data. Obviously what I can do as well, come back out of that, is actually save this data using the mem button, and then this gives you the object number and the test number. You can change that with these arrows here. If I hit the mem button again, and it saves that test, so that data is now saved and can either be recalled back on the instrument or downloaded using the computer software. That's those first two methods there. To demonstrate the third method, I'll have to get the computer out and hook it up to the insulation tester. And our final way of capturing PI tests with this instrument is to hook it up to the computer. Now obviously we are on an old RS232 interface here, so what I actually have is an edge port USB to RS232 converter. Works fine with that, although you do need a null modem balance lead between the two to get it to communicate. You can see hopefully on the computer screen we are running the PI test on there, and you can see the meter is merrily winding up. We've got 38 seconds to go on this. The only thing to note is we are limited with the buttons. We cannot stop the test whilst we're on COM. Our R, DAR and pi doesn't work. Our voltage time doesn't work. The instrument is totally locked out when you're running it from the computer, so the only way you can stop the test will be to yank off the leads, switch off the set, or stop it using the software. Not a big problem, just something to be aware of while you're doing that. And obviously our test is over now, but even if I press the buttons now, I can't do anything with the instrument. Even the backlight doesn't work whilst you're hooked up to the computer. We've got the end of our results there. We dial was 1.63, 30 seconds, 60 seconds reading, and our pi, that all done. However, whilst I have got the plot here on the screen, I can't get to any interval test data. We do get down the side here, we've missed the PI value, which is interesting. Okay, so that's probably something to do with the charged circuit. Again, I didn't release it quick enough. If you notice down on the left hand side, I've missed the PI value off. We've got the 1 minute. We don't have the 10 minute, consequently we don't have the PI value. Okay, that's interesting. To set the test up, you go to configuration, and there you can see that's how I've set the circuit up for the test. This, again, all derived from the computer. The advantage with this is you've got the whole setup menu right in front of you, whereas you have to go through it screen by screen if you're on the actual instrument itself. So classic demonstration for the use of the guard terminal with a terminal bushing. You see we are running at a 1000 volt test at the moment, and we have 831 mega ohms. I'm connected to the top of the termination up here and down at the base of the bushing down there. So we're getting an insulation reading of the circuit under test and the leakage over the surface of the bushing. So I just stop that so I don't zap myself, and then I'll apply the guard terminal clip here around this lead that's wrapped around bushing itself. See, that's there, and now we'll go for a repeat of the test. We'll let that start off, and we should get a value much closer to 1 gigaohm, and there you have it, 196 mega ohms. So that's the guard terminal now, taking away any of the leakage current over the surface of the bushing and removing it from the resistance reading that it's given. So as I said, classic demonstration for the use of the guard terminal there, and seems to be working fine on this CA6543. So we'll finish this off trying to measure the 2 tera ohm resistor that's in this box. That's the largest resistance that I actually have as available as a test resistor. I've set this up on 500 volts with the guard terminal is put in there as well. I've set the resistor up to utilise the guard terminal because of such a high value and the low current that you're trying to read. And as you can see there, we are reading 1.9 tera ohms, so that's pretty much within spec, 5% resistor in there. But there you go, that's the CA6543. Obviously quite a niche instrument really, given the actual cost of it and its test capabilities. But for me, for a top-of-the-range insulation tester these days. The RS232 is a bit of an amusing interface for it to have. It is missing a variable test voltage range. I know you've got the 5 fixed voltages there, but for me, an instrument of this specification should really have a variable voltage as well. It does have a little bag on the top to store all the leads in. However, with the leads stored in that in bits and pieces, it does tip the instrument over with the lid open. So that's another little gripe of mine. But other than that, I say it is a high-spec instrument, pretty accurate. Certainly meets my needs. The addition of a guarded test lead I have use for, and also the guard term itself, you've seen me use that. But yeah, that's the CA6543 insulation tester from Chauvin Arnoux. Hope you found the video useful. Thanks very much for watching, and I'll see you again in the next one.